Hello, everyone, and welcome to another episode of the GC 100 podcast. I'm your instructor and host, Dr. VG. All right, today we're going to continue our journey from Earth-Sun geometry and use that to better understand electromagnetic radiation in our atmosphere. So, how this looks, just going to check one thing. Okay. We're going to begin looking at the electromagnetic spectrum and use that to then kind of think critically about our atmosphere before turning our attention into global radiation, which kind of leads us into some of our next lecture topics. All right, so electromagnetic energy here is transmitted in waves and travels away from a surface of an object. So I'm emitting electromagnetic radiation, so are you, even your desk or a fire or the heater. So many different objects emit electromagnetic radiation, and they are all traveling in waves where some energy has higher frequency, meaning the time between crests is shorter, or lower frequency. So let's explore some of those properties of wavelengths here. So wavelength is measured as the distance between crests. So from one crest to the next is a wavelength, and that's the distance. So there's a long wavelength energy and very short wavelength energy, and our short wavelength energy is our high energy, and our long wavelength is our low energy. More on that here soon. We can also measure the height and here the amplitude of a wave. And so the amplitude is the distance between the equilibrium point, which would be a line going right through the middle here. And so the distance between the equilibrium and the crest is the amplitude. Wave height then would be the distance between the crest and the trough. And we'll come back and explore more about electromagnetic radiation throughout this semester. And so here, the spectrum is the entire range of radiant energy produced by the sun. And so the sun produces an incredible amount of energy in many different forms, or in this case, as we'll separate them by wavelength. Before we turn our attention to the sun, I thought I'd do a throwback to my childhood and these original black and white Godzilla videos. So does anyone know what type of electromagnetic radiation that Godzilla emitted? Was it a Zilla wave? Well, if you answered gamma rays, you would be correct. Back to our regularly scheduled program. All right, so here are the basics of the electromagnetic spectrum. So it's measured in successive wavelengths, so divisions of wavelengths into several categories. Each of the major divisions here showed on the screen, and I'll kind of further break this out into subcomponents, beginning with shortwave radiation. And so what we consider shortwave radiation is radiation that's emitted by hot objects. And we'll talk about what that specifically means, hot object, here in the coming slides. But for now, a hot object like the sun is capable of emitting shortwave radiation. And so this is short, very small wavelength. So the distance between crest and crest is very short, and the frequency, the time between those crests as it is received by a sensor or by you, is incredibly small. So this short, high energy radiation is only emitted by hot objects. Something like the sun is only capable of emitting shortwave radiation. We, humans, Earth's surface, a warm rock, is not capable of emitting shortwave radiation. So some of the major forms of shortwave radiation include gamma rays, like Godzilla, X-rays, ultraviolet rays, which are wavelengths just shorter in terms of wavelength than visible light. So visible light being emitted by a hot object. And then here are near infrared. And so there's a component called thermal infrared, which is a long wave radiation form next. But here, near infrared radiation is radiation that's just longer than visible light, so one of the short forms of short-wave radiation, and it occupies this wavelength range. In terms of moving forward, quizzes, exams, assessments, etc., there will be no requirement. I don't expect that you memorize these ranges specifically, but I would like you to focus your attention on understanding or identifying which forms of radiation are short wave and which forms of radiation are considered to be long wave radiation. So these are only emitted by cooler surfaces like Earth's surface, like a hot beach when you walk on it, for example. And so here, long wave radiation emitted by cooler sources include thermal infrared energy. And so this is a form of infrared energy, and it is in fact sensible heat. We'll get back to that later this semester. But here, thermal infrared energy being slightly longer in wavelength than near infrared, and here again, just a little bit longer than visible light. So it's energy that's just a little bit beyond what we can see with our human eyes. Beyond thermal infrared energy, we have the form of microwaves, radar, TV, and radio, and some radio waves having incredibly long distance in the hundreds to thousands of meters between wavelength. In fact, that makes me think of what a network of emission of what's called extreme or what was it, ELF, extreme low frequency radiation. So we actually connected a bunch of wells to Earth's surface to make a satellite dish many years ago, and we emitted these extremely long forms of radio waves using the bedrock of the Earth as the dish or the emitter, and those wavelengths, in fact, had thousands and thousands of meters. They were kilometers in distance, and the distance of the wavelength actually would go to the top of the atmosphere and all the way down to the deepest part of the ocean, allowing us to communicate literally through basic like Morse code signals from here in Michigan and northern Wisconsin with submarines on the other side of the Earth. Kind of cool. Check it out if you're interested in learning more about that. All right, so back to our regularly scheduled program again. So here we have shortwave radiation emitted by hot objects, and then we have long wave radiation emitted by cool objects. So now let's think a little bit more about hot and cool objects, knowing that only hot objects here, for the case of this lecture topic, are emitting shortwave and cooler objects emitting long wave. And so the sun, considered a hot object, emits mostly shortwave radiation. In this case, something like the sun emits an incredible amount of radiation in all forms of the electromagnetic spectrum, including long wave radiation. But if you are actually to quantify in terms of units of energy, the amount of energy released by the sun, most of that energy is in the form of these shortwave forms of radiation. So the sun is emitting all of these shortwave forms of radiation, where the Earth, a cool object, is emitting energy mostly as long wave radiation. So the majority of Earth's surface here is emitting energy, and largely here emitting energy in kind of our thermal infrared spectrum. So in terms of quantities, the sun emits an incredible amount of radiation, much, much, much more than the Earth, where the Earth emits a much smaller amount of radiation total than the sun. So this kind of ties into some basic physics properties, or here the Stefan-Boltzmann law, where a hotter object emits more energy than a cooler object. Really and ultimately the majority of energy released by Earth's surface. So think about like walking, you could be on pavement, but let's think of natural surface, like you're on a rock or at the beach, the sun's out, that radiation from the sun is received by the beach or by the rock, it warms up, literally it's absorbing the energy, and then it's re-releasing that energy that originally came from the sun as thermal infrared energy, as sensible heat that we can actually sense, touch, and measure. And so most of the energy released by the Earth was originated from the sun. There's other forms, so like magma, volcanic fusion within the Earth is also generating energy. We'll talk about Earth's interior structure later this semester. So there is some other form of energy released by the Earth, but comparatively, in terms of like an energy budget, how much energy is released at Earth's surface by the Earth, the majority of it is actually recycled, if you will. We'll talk about that later, where it's like really the amount that was absorbed by the sun and then re-radiated or released. So in terms of hot objects in the sun here, it's produced by nuclear fusion and it's emitted as electromagnetic radiation. So nuclear fusion within the sun is producing energy and then it's emitting, casting these waves outward into space in all directions in the forms of electromagnetic radiation. The sun, in fact, produces nearly a constant rate of radiation. So that emission of electromagnetic radiation is essentially constant. While there is some variance within that, the amount of energy can vary a little bit, mostly due to what we know as sunspots, which we'll talk a little bit about this semester. But effectively, there might be spots on the sun that produce instantaneously at that moment much more energy, but effectively out in space away from the sun, that amount of energy being emitted by the sun is constant at all times, which is known as the solar constant. So the solar energy received at the top of our atmosphere is really just always the same. There might be these very episodic or incredibly short-term events that more energy is received and that causes interference with our satellites, and it even creates what we know as the northern lights. Also, more on that later this semester. But 99.99% of the time, the amount of energy received at the top of Earth's atmosphere is constant, and that's known as the solar constant. And so that energy traveling from the sun out and away at the distance of the edge of the Earth's atmosphere, the sun is coming in a straight line at its fixed position, which is Earth in space, and that amount is approximately 1,370 or 1,370 watts per meter squared. And so at all times when the sun or when the Earth is receiving energy, we're receiving exactly that much. So now moving forward within this lecture and also future lectures, we're going to start to think about what happens to that constant amount of energy between the top of the atmosphere and Earth's surface. How does that differ from one location to another and then over time? So now let's begin this journey, or kind of continue this journey rather, where we're going to think about the composition of Earth's atmosphere and how that interacts with electromagnetic radiation. So I want to know, what is atmosphere? Can you provide a definition of it for me? And if you thought it was the independent hip hop group based out of Minneapolis, I'm afraid you are incorrect. However, for real this time, the atmosphere is the medium through which radiation flows on the way to Earth's surface. So again, the solar constant radiation reaching the edge of Earth's atmosphere, and then between the top of Earth's atmosphere and the surface, there is this thing called air, and that air has varied composition. We'll talk more about the different composition of Earth's atmosphere in these major layers in a future lecture topic. But for here, we're just going to kind of think about the atmosphere in general and what it consists of. And so the composition of our air, our atmosphere, is in fact unique within our solar system and beyond. And major components of this unique composition include both oxygen, which we're breathing, as well as carbon dioxide, essential to all life on Earth, as all of the plants require CO2 to facilitate photosynthesis. The composition of Earth's atmosphere, CO2 among other constituents, other molecules, in fact, shield Earth from an incredible amount of very high energy forms of shortwave radiation. And we'll talk more about ozone and the stratosphere later, but really the stratosphere and the ozone contained within the stratosphere provides us this remarkable protection from Earth's radiation, including these extremely high energy forms like UV, extreme UV, so UVA, B, and C. There's three forms of UV radiation, and X-rays and even more higher forms. And so a lot of that, in fact, is shielded here by the stratosphere. So what are the two most abundant gases in our atmosphere? They are nitrogen and oxygen, and actually nitrogen being the most abundant and then oxygen second. And beyond being abundant, both nitrogen and oxygen are what are known as constant gases. This also includes the gas argon. So all three, nitrogen, oxygen, and argon, the concentrations in our atmosphere remain relatively consistent over time and across space, meaning the concentration is essentially always the same everywhere at all times. There's very little variation. There's a little bit, but it is very minor when compared to what we refer to as variable gases, where the concentrations of gases such as carbon dioxide, water vapor, and ozone have quite a bit of variability, and some of them significant variability over time and across space. So let's explore some of these variable gases a little bit here. Water vapor is an incredible absorber of heat energy. In fact, that makes it a greenhouse gas, and a powerful or potent greenhouse gas at that. So water vapor is highly variable across space and over time. And so it also moves. And so this is one of the most profound aspects of kind of thinking about energy on Earth and the transfer of energy both across space and over time, where areas in the tropics near the ocean, where there's a lot of atmospheric moisture, because near the tropics there's a lot of ocean, so there's a lot of evaporation and a lot of water vapor in the air, then absorbs an incredible amount of radiation from the sun. And due to global circulation patterns, which we'll learn about later, you can move that energy that was absorbed across many degrees of latitude, even like all the way up to where we live in some instances when air masses move from the tropics all the way up into the mid-latitudes. Not always, but it can happen. And so that then has profound influence on atmospheric temperature. So appreciate that water vapor absorbs energy from the sun, and it also moves with global circulation patterns, and the variability then comes in. Some locations like semi-arid and arid regions near deserts have very little amounts of atmospheric moisture, and then areas near coasts, including here our kind of Great Lakes region, have much more or more abundant amounts of moisture in the atmosphere. This can also change with atmospheric pressure, but we'll talk more about that later. Okay, so moving on to carbon dioxide, another variable gas. Carbon dioxide essential to life via photosynthesis, and similarly here, carbon dioxide contributing to what is known as the greenhouse effect, which we'll define later, and this is very much a natural phenomenon, natural process. The greenhouse effect, which is effectively capturing, absorbing solar radiation, storing it, and re-radiating it as long wave or thermal infrared radiation. So carbon dioxide, a variable gas in our atmosphere that is a greenhouse gas, it contributes to the greenhouse effect. The current composition as percent is 0.04%, which is about 420, 425 parts per million, and then we're rising due to industrial activity. And so our concentration of carbon dioxide in our atmosphere has continued to increase really for the last many decades and even over 100 years, and it continues to increase. And because it's increasing, we're increasing that solar forcing or heating component where, again, carbon dioxide is capable of absorbing radiation and contributing to the greenhouse effect. More on that later. So let's move and turn our attention to ozone, another highly variable gas in our atmosphere. And ozone can occur both near ground level, so here in the troposphere, near Earth's surface, And in that case, it's really a form of pollution, as it is not good or not healthy for humans to inhale ozone. However, ozone is essential for life on Earth. It's essential for us and for plants. It provides in upper atmosphere, in the stratosphere, it provides us with this incredible shielding from all forms, including UV and X-ray, so high energy forms of radiation that ozone is literally absorbing and shielding us here down lower, where some of that radiation does make it through, but it absorbs and shields us from an incredible amount. And without that, we would have incredibly high rates of skin cancer, and plants would wilt, and it would have innumerable consequences, including really drastically affecting the atmospheric temperature here lower in Earth's atmosphere. So many years ago now, in fact, in 1987, there was the Montreal Protocol, which limited the production of chlorofluorocarbons. You may have heard of this before, and how CFCs, or chlorofluorocarbons, break down ozone, which is O3, and it breaks it down into oxygen and to chlorine dioxide. And so one CFC, which is a component that we used to use in refrigerants, like in your refrigerator. And when that CFC leaked out of a refrigerant and then into our atmosphere and made its way up into the stratosphere, that one CFC molecule can break down many, like thousands of ozone molecules. Going back to this slide, ozone literally here in the stratosphere, protecting us, shielding us from an incredible amount of ultraviolet and other forms of shortwave radiation. And so due to this, there was an incredible depletion of the ozone layer, and it happened across the globe, but was highly concentrated here near Antarctica, and so then in the Antarctic Circle. And so as CFC moves with global circulation, and then we have separation of these climate zones, what's called the polar or Antarctic polar vortex here will kind of like trap the CFCs in this region in certain portions of the year, the spring for the southern hemisphere, and then voila, you have this like perfect melting pot where literally you have a whole high concentration of CFCs now trapped where it's not exchanging with the rest of the Earth's atmosphere, and it causes a tremendous breakdown of ozone, and then that has much longer term, longer and bigger, small scale but large area gradient. So it affects climate across large distances of Earth's surface. So with that, there is a really great video that we can watch where you could click here and you can then kind of better understand both like what happened with the Montreal Protocol and what the consequences were and could have been, but also linkages between ozone, between CFC, our atmosphere, and climate change, meaning like changing climates. Literally, this CFCs did in fact change climates. There's many forms of climate change, and that ultimately just means what was normal for an area now is normal, or it's different. Areas that receive some rain receive more rain, or areas that receive some rain now receive less rain. Areas that were this temperature get slightly warmer or colder. And then as we move here pretty soon in the course into global circulation patterns, it really can happen on these latitudinal gradients where you see many of the Earth's deserts in the subtropics, and we'll talk about why later, and how that then will shift north or south, these patterns with perturbations or disturbances. And so this is a form of a disturbance that caused climates to change. All right, so now we're going to connect Earth-Sun geometry, electromagnetic radiation, the composition of Earth's atmosphere, and we're going to integrate it here into some global radiation balance, as that then kind of prepares us for future lecture topics. So here, another major player, if you will, or influence with our atmosphere are microscopic particles, particulates that are carried in the air. So a particulate is a microscopic particle that's in our air, and it can take both liquid and solid forms. So examples of that include liquid forms like clouds and rain, and then solid forms, snow or hail, pollutants, spray, soil dust, smoke, ash, pollen grains, salt spray, as I meant to say before. So these are all formed like literally microscopic particles within our atmosphere. They are highly influential as they're solid, literally like smoke, ash, little particulate dust can absorb energy just like the beach does. It's just a tiny particle, but it is absorbing energy in the atmosphere. It also forms the nucleus, like cloud seeding. It forms the nucleus for precipitation. Where there's a particle, then condensation can occur, and where you have lots of tiny particulates spread across the region, like a dust storm, that then forms cloud seeding. You can literally like seed a cloud, or naturally or man-made. These absorb energy, as I just said, and then in terms like lower in the atmosphere, dust storms, pollution, etc., smoke, ash, these all can have negative health consequences. So I'd like to now like really focus on and define what is the greenhouse effect. The greenhouse effect is where the atmosphere absorbs shortwave radiation emitted from the sun, as well as just appreciate that the sun also emits forms of long radiation, but in terms of the amount of energy received here as the solar constant, most of it is shortwave because hot objects emit more energy in the forms of shortwave radiation. And so atmosphere absorbing shortwave radiation from the sun, and then within the atmosphere, that is captured temporarily, absorbed, and re-radiated, and then that re-radiation can happen again and again and again, where, let's say, for example, if you take a rock and you put it near a fire and that rock heats up, and then you take the rock carefully, it might be really hot, and you move it next to another rock that's colder or even touching, that then like rock you heated up is going to heat up the next rock, and then that next rock, and so on and so forth. Similarly, within our atmosphere, we can receive shortwave radiation. It can be absorbed by a singular CO2 molecule. That molecule could then re-radiate that energy, and that long wave radiation can then be absorbed by another CO2 molecule, or by ozone, or by another greenhouse gas like water vapor, and then that can be re-radiated, and that can happen again and again. And that process is known as counter radiation. It's this form of redirecting energy back to Earth's surface. And so it's this kind of recycling of absorption, emission, et cetera, et cetera. And I'd like to kind of just really emphasize this is a natural phenomenon. We are all here because of the greenhouse effect. Earth would be incredibly inhabitable without the greenhouse effect. And so we want this. It is essential to all life on Earth. However, as we are influencing the atmospheric composition due to constituents like carbon dioxide and other greenhouse gases and other components, particulates, wildfires, natural or man-caused. Anyway, so as we influence the composition of Earth's atmosphere, we fear that that could have too much greenhouse effect, and we just really don't know what will or won't happen. We think, and we have projections and models, and many of them have unfortunately be becoming true over time here as modeling and future forecast has occurred. But anyways, just kind of appreciate that we're in this like fine balance. We want the greenhouse effect and counter radiation, but as we influence the composition of our atmosphere, we're then influencing the greenhouse effect, making it like more vigorous, so to speak. And is there a point where there's too much? Or on the contrary, is there a point where there's not enough? And so without the greenhouse effect, our atmosphere, our conditions near Earth's surface would be a lot more like Mars, where it may be warm-ish during the day, but incredibly cold at night and ultimately inhabitable. And so with that, Dr. VG is signing off.